Hello everyone, and welcome to Live from the Lab. This is a show where we talk about different technologies that Bruker's developed in order to help scientists discover the world around us. Today's topic is about optical emission spectrometry. That's a little bit different than our typical X-ray topic, and in this case we're going to learn exactly why you would use an optical technique instead of using an X-ray technique. But like we say, it's always good to have the right tool for the right job. So in order to learn more, though, about OES and one of our newest products, the Q6 Newton, we're going to hear from the product manager. We're going to see it in a commercial and also in a lab demonstration. And then we're going to answer any of your questions that you have live here on the air. So with that, let's see this thing in the commercial. All right, thanks everybody for joining us today again. Now I am joined by the product manager for the Newton, Peter Poplewski.
Hi, John. Hi, everybody.
So Peter, you're located over in Germany, right?
That's right, and I'm located here currently in the lab in Karlsruhe. Yeah.
All right, so is that really the lab, or is that just a
that is really background? That is really the lab, and the background is also real. So that's not a fake system. That's a real Q6 Newton behind me.
All right. So the Q6 Newton now, that's the latest member kind of our industrial elemental analysis family. So we have XRF tools. We also have OES tools. We have all these different systems set up for that industrial environment. Why is it that somebody would choose, say, an X-ray technique or an optical emission spectrometry technique?
You see, when you're working in the industry and you have strict requirements on speed, operational costs, sample preparation that shall be low, and you need to do metal analysis, then there's no way around optical emission spectrometry, because that technique can do the job in very short time, below 20 seconds, give you the full elemental analysis of your alloy with very low operational costs and very fast, high precision. Yeah, that's the way to go. That's a workhorse for metal analysis. So you have then to choose the right tool for the right job.
So now you had said this is a metal analyzer. So what would our typical, say, use scenario look like?
The typical, these are different ones. That we have, of course, the primary metal manufacturers, big steel plants or smelters, something like this. Then if you go through the value chain, you have the guys, for example, mechanical engineers that are building cars, other tools out of this, and you have control labs. You have, let's say, everything where metals are used. It cannot even go through customs for metal inspection and positive material identification. Is that the right grade or is it not the right grade that client supplied me or not? So you cannot
things like, for
difference.
example, checking the amount of chrome in a stainless steel. This would be an example where you might use it.
That would be an example, but that is I think a task that XRF also can do. But if you want, for example, to sort on the low alloy steels where the carbon concentration matters and you want to do it fast, then XRF is not capable to do this in that speed with that required precision. Then you need to go for OES, for example.
And now the other motivating factor sometimes for people to use this technique is norms, right? Sometimes it's just, this is how things are done. You have to use an OES for it.
That's correct.
Enough said.
Sure. That's always correct.
Yeah. That's the way it is. That's the way it is. So now, speaking about the machine itself, so the Q6 Newton, one of the big questions I think people always have out there is what motivates the development? Why did Bruker say, you know what, we've got a nice family of solutions in OES. I mean, we're well known for those. Why do we need to add a new member to that family of solutions? So why did we have to develop a Q6 Newton? I know it's a tough one for
because of course we are striving for perfection and we always want to get better, and not stay there with older developments, although these are also further developed with new calibrations and so on. But if you, at a certain point, you run into the innovation cycle of IT and electronic components, and at a certain time, you will run into product obsolescence and you will have difficulties to support that platform for the next 20 years and so on. And if you want to really introduce new concepts, what we did here with the Newton, then you would really need to make something new from scratch. And that's what we achieved here and what was developed here. For example, the complete new electronic platform, which is now under Bruker control, no third party involved. It's the same Alaska platform shared with the other AXS products, so the X-ray product line. It's now in our hand, and that is a platform for the next 20 years of reliable OES systems.
So since you mentioned the software, I know that's one of those very important things because, yes, everybody touches the hardware, but at the same point, people are interacting with that software. And I know here you guys have worked really hard to make it easy to use and also just the results easy to interpret.
That's right. And it took, of course, also some software development, but in firmware, to make that new system, the new hardware, operatable by the software, because our software operates all OES systems, the older ones, but also the brand new Q6 Newton. And a lot of departments.
So then in terms of now the system, it's a benchtop solution. So the nice thing about that is that it can really be deployed anywhere, right? That could be on a foundry floor, that could be in a lab.
Yeah, it is. You see it behind me. The Q6 Newton is our highest end desktop model for optical emission spectrometry, but we have, of course, also the big high-end floor standing Q8 Magellan. That is what you normally find in a laboratory of a steel plant in a QA or QC laboratory. But the desktop systems, they also find their place in foundries, mid-size, small size, and they are also withstand harsh environments. So they are robust in that regard.
So speaking of those environments, one of the big innovations here was this shielding it from the environment in terms of temperature, right? And getting this system so it's stable at all times. So tell us a little bit about what went into that development.
So I do not know if you know, but our, let's say, smaller desktop systems, they have a patented feature called AAC, that stands for Automatic Ambient Compensation. And what that means is we have something that we call a compensation tube in, and the entrance lid is mounted on that tube, and that grows or shrinks and compensates the thermal expansion of the spectrometer housing. Because in the spectrometer housing, you have the grading, the diffraction grading, and the distance is very important because that is makes a focus of the system. It's like what you have on your camera, and you adjust the picture to be sharp. And that is automatically achieved by this patented Bruker feature. But on the bigger systems, and the focal length of the optic in the Newton is bigger than on the smaller systems, way bigger, and we have two optical systems in, you need temperature stabilization. These compensation tubes do not work with that high focal length. Mm-hmm. And temperature stabilization means stability, analytical stability. So now, how did we achieve this analytical stability and temperature stability? It's the entire system, or the optics are embedded in an isolating form. It's a really hard form. And this form also has molded in air channels. So we pump, let's say, conditioned and temperaturized air around the spectrometer module and all the components in the system. And then in the back of the system, we have this, let's say, air condition that can heat and cool the system. So, and with the insulation and the active heating and cooling, and we are able then to hold the temperature constant at a wide ambient range. Also, fluctuations are covered, and the span is plus minus 0.2 degrees Celsius. So that's really stable.
It sounds like it. Now, speaking of stability, another important bit is to have a nice stable spark platform. And that's what you've got with this Smart Spark, right?
Yeah, Smart Spark is not only the, let's say, the analytical table, the spark stand plate, but relates also to the source generator, our Smart Spark source, because that has also been improved or completely new designed, beginning with the Q4 Polo and now further improved with the Q6 Newton. And that is more precise now than also the spark curves. The form, the exact form of the source curve of the energy is now matching. The output is what we require as an input. So there is no deviation anymore. And also that is equipped with a safeguard mechanism that is monitoring the plasma condition continuously, which eats a single spark.
So now kind of to go to the end of that chain, you got the detectors. And here we saw in the video that we have this new HighSense detecting. What is special about HighSense? What makes it have high sensitivity?
It's not the detector chip alone, because it's the entire readout chain that plays the role here, and this makes it HighSense. It's the latest actual development. It's our own development. The linear area sensors that we use are also latest technology. We don't develop them on our own, but these are latest CMOS-based detectors with a very good quantum efficiency, especially in the vacuum UV range. And that is where we see the benefit directly in LOD. And together with our high-speed readout electronics, you see the benefit in the short measurement time.
So it sounds like we've kind of got that whole package then, all the way from spark through detection, stability. I mean, it's kind of everything in that nice compact footprint.
Everything is new in that system. That's correct.
All right. So I think everybody out there would probably like to see this thing in action. And in order to see it in action, we've put together a demonstration of it. So let's head on over and see it. And then, by the way, if anybody has any questions, go ahead, just type those in the side of your screen right now, and we'll get to those right after the demo.
Rapid, reliable, and always ready. These are the words we use to define the Q6 Newton. And today, we are thrilled to share the state-of-the-art optical emission spectrometer with you. Our development team put a lot of effort into developing the Q6 Newton, which resulted in a powerful yet reliable instrument that exceeds the industry standards and provides accurate and efficient elemental analysis. My colleagues have already discussed various features of the system and explained the development process of this magnificent optical emission spectrometer. But, as the renowned physicist Carl Sagan once said, extraordinary claims require extraordinary evidence. So, without any further ado, let's analyze some samples and have a closer look at the performance of the Q6 Newton. So here on the Sparks template, I have an ultra-low carbon steel sample. I will press the green button to start the analysis. Here we will see how fast the Q6 Newton analyzes a sample. And again, this is thanks to HighSense detection technology and all the new electronics that we have implemented inside. And for the level eye, we have a specialized method with which you can analyze a low alloy sample under 20 seconds, as you have just seen here. So I will remove the sample and clean the tip of the electrode, rotate it, place it again, and start the second analysis. So these new electronics allow us to acquire, transmit, and process the data at a much faster rate, while the Smart Spark technology provides the optimum excitation parameters and creates the plasma. Now we have the second analysis done. Let's clean the electrode, rotate the sample a little bit, and start the third measurement. And of course, during the analysis, our argon shield technology ensures a stable plasma and also protects both UV and the fiber optic windows from the metal dust. This is thanks to its intelligent argon flow design under the Sparks template. Now the third measurement has just finished, and we see all three measurements on the screen, so you can see the excellent precision of the system and repeatability. So I will continue with a cast iron sample. So I will remove the sample, clean the tip of the electrode, and position the sample here and start the analysis. Now we have seen how fast the Q6 Newton can actually be. However, it's not only fast but also reliable, and this reliability also means short-term and long-term thermal stability. This is where our rock-steady design comes into play. Rock-steady technology rapidly increases or decreases the system's internal temperature to the optimum level and ensures that it stays at that level. This thermal stability, of course, translates into the analytical stability as well. Now we have the first measurement. Let's go for the second one. When we designed the Q6 Newton, we also considered our current users. We wanted them to be able to use their existing sample adapters with the all-new Q6 Newton. This means that if you have a thin wire adapter or a thick wire adapter or a small sample adapter or a metal sheet adapter, you can analyze your samples using all these sample adapters with the Q6 Newton as well. So the second measurement is done. Let's go for the third one. Besides improving the Q6 Newton's analytical performance, we also thought about how to make an operator's daily analysis routine easier. With this in mind, we developed this multi-purpose button that you see on the system. So it not only starts and stops the analysis, but also communicates with you to give you information about the system's actual status. Steady green means ready to analyze, and it turns steady red during the analysis, as you see here. And if it's steady blue color, it's flashing the UV optics. If it's white, it means that the elemental switch is not connected at that moment. It will turn yellow, for example, when it's in the service mode, when you clean the spark stand plate. If it's blinking red, which means that there's an error, for example, this might be caused by the low argon pressure in the argon bottle. So even if you're not working on the system and you are on the far side of the laboratory, this Q6 Newton will be still communicating with you from afar. So we have finished analyzing the cast iron sample, and you can see the results on the screen, and you witnessed the excellent precision of the Q6 Newton. And of course, the smart buttons functionalities are not limited to communication. If you need to lower the sample clamp without starting the analysis to position your oddly shaped samples, for example, all you have to do is to press this button just a little longer, and the moment you release the button, the clamp will go down, but it will not start the analysis. So to lift it up, you have to do the same thing. And you can also use the smart button to flash your UV optics, and this is done by pressing this button more than 5 seconds, and it will automatically start flashing the UV optics without the need of an external PC. So this was the first look at the Q6 Newton in a nutshell. Now it's time to go to the Q&A session, and I will see you there.
Here we go. All right, so here we are. We're back in the studio and the lab, and now we are joined by Okan.
Hi, John.
Hello. And of course, Peter is still here. So we are all here to answer any of your questions that come in. So on the side of the screen, like I said, if you're watching YouTube right now, you can go ahead, just type your question in and we'll answer that live. Otherwise, we do have some questions that have come in before. If you are watching this video later, or if we don't get to your question, or next time you see a live from the lab you're interested in and you happen to have a question, you can send it in to live.events@bruker.com. And we will answer that here live. So, and in speaking of live, we'll start off with one of those questions that came in. And this is from Belen. Hello, at INTI in Argentina, we have a Q4 Tasman that we use to verify compliance. So thanks for being a Bruker customer out there. Can you talk about precision and nitrogen analysis in steel alloys? So I think that's two questions. One is just, can you say something to the point of precision? And then also, could you tell us a little bit about nitrogen analysis for steel alloys?
Take that. Okay. So yeah, the nitrogen analysis is really important in steels, and the Q6 Newton does a really excellent job on that. So basically, okay, of course, I think she's asking about the precision, right? So the precision will always depend on the concentration level, and different steels, different alloys, we will have different levels of nitrogen. Thus, the precision or the standard deviation will depend on the concentration level. So for that reason, it's difficult to say something or give some numbers. But what I can say, if I'm not remembering wrong, I think it was around 1% RSD. So this is one of the numbers that I remember from our application report that we recently released. And if you want to take a look at that report, please get in touch with us, and we can gladly send a copy to you so you can see the performance of the system. We analyze different alloys, different steels in the iron base, and there will be some other application notes coming up for aluminum and copper matrices as well. So, but to sum up, I can say that I think for 250 ppm, that's what I remember, it was around 5 ppm, 3 to 5 ppm, something. It's something like 1% RSD. Yeah.
May I add something here?
Yeah.
Yeah, go ahead.
I heard the word certification in that question. So it is important that client has CRM material available to check the results and the accuracy there. Concerning the precision, don't forget about the argon supply and the purity there. Especially for trace analysis, and often in steels, you need to control the nitrogen level at 100 ppm or even below level, you would need really Argon 5.0 or better quality and or a purifier. So the standard quality for argon spectrometer for spectroscopy for OAS is 4.8. That means 99.998% purity. In other words, 20 ppm, volume ppm contamination possible. So, and then if we think how argon is produced, it is, you have about 1% per volume percent natural abundance in air. 1% is argon. So this is how they generate, or how they generate the argon by air liquefaction. So what will be the main contaminant of that? Nitrogen. So you can expect that maximum maybe 10 ppm of that 20 ppm contaminations is in form of nitrogen. Maybe 2 to 5 ppm is oxygen, and then you have a little bit humidity, so water in it, and that's basically the contaminants in argon. So, and then it's you need to know that the nitrogen, if it's already in the gaseous form as a contaminant in argon, is a way higher factor than if it is included in steel. So 1 volume ppm of contamination in argon is good to show you a response that would correspond to 20 to 50 ppm in your material, because you do not need to melt it or to ablate it from the metal. That directly excites the nitrogen in the argon, and that will give you a huge background. So and if you really have 10 ppm in, multiply that by 20, then you have a background that is equal to 200 ppm. And that will make it very hard and unprecise then if you want to control 10 ppm. It's possible, but these 200 need to be absolutely constant. I think it's mathematically it's clear. It's 1005 minus 1000 is 5. It's the same like 5 minus 0. But the first case is very hard to differentiate, and because the relative change is so small.
But the rule of thumb is the lower the nitrogen concentration, use a better quality argon. That's the rule of thumb.
Right. All right. So, and then just some clarifying questions. Just that Belen we only have a CRM with nitrogen and stainless steel alloys, and I understand the importance of the purity of argon. We used 5.0 purity, but we have to control it. So all very good points. Now, one thing though, one maybe intricacy, I think for my information and for maybe anybody out there wondering, in terms of precision, how does the Q6 compare to the Q4? Tasman. So they said that they had a Q4 Tasman right now. If they were to say replace it with a Q6 Newton, would they get better precision, similar precision, because these factors, say, that you were just talking about, are the bigger weighting factor?
Let's say if it's not argon quality or so is the reason of it, you will get better precision, way better precision with the Q6 Newton. The reason is nitrogen is a line that is deep in the UV, and especially in the deep UV range. One prominent line is at 174 nanometers, for example. But I think we're also using one even deeper in the UV for that. Their quantum efficiency matters, signal to noise matters, and there the HighSense detection system in the Q6 Newton is way more advanced than the traditional one that we use in the Q4 Tasman.
All right, and speaking of detectors, actually we have a question I had come in before from Kyle. what detector technology do you use in your OES systems, PMTs, CCDs, or CMOSs?
In short, all of them.
We use it all.
We use them all in different systems. We have a complete portfolio available. For example, PMTs, photomultiplier tubes, are the traditional detectors there. They were existing first and developed first. They have been further developed, and they are still reserved for our high-end Q8 Magellan system. That is, you have a dedicated detector, a dedicated tube for each individual elemental eye. The benefit of these is they are incredible fast, and they allow you to do time-resolved spectroscopy. That is something you cannot do with silicon-based detectors currently, not out of the box. For example, both CCDs and also the latest CMOS technology does not allow to do single spark evaluation or time-resolved spectroscopy. The reason is that on the silicon-based, you have always a clock rate where you have to empty the charge from the transistors that sample the charge, and you can change the clock speed, and the charge needs to drift through the silicon, and that's not fast enough for that because the time scale is too low. And then we have, apart from the PMTs, then we have this linear array, the silicon-based linear array sensors, where the older development and the beginning was CCD. They are still not bad and have their right to live and are competitive. But if you do a new development, like we did with Q6 Newton, you choose the latest technology, and the latest technology is CMOS, and it has, of course, some benefits, especially the speed and especially the quantum efficiency in the UV range without any scintillator coating also. So we use all what is available.
All right, there we go. So next question from Chi is, can I extend the calibration range on certain elements myself?
I'll get that. So the short answer is yes. Yes, you can. But it always depends on the availability of the CRMs, right? So our calibration is done in a way to cover most common alloys in all the available matrices. But if there's a need for calibration extension, we can do that either here in Germany before we ship the system, given that the samples are provided, the certified reference materials, or this can also be done on site with the help of applications, right? So yeah, technically it's possible to extend the ranges. Yeah.
So now in terms of support, support's a very, very important topic, especially industrial application. What kind of support do we offer? Is it that somebody always has to come on site, fix these things? Can we fix things remotely? Do we offer any free support, or is it always paid support?
So, okay, so the first step of our support scheme is actually the remote connection. So what we can do is remotely connect to the PC of the system and just check the log files to understand what's going on. If there's something wrong with the system, sometimes it's just a sample preparation. Sometimes there's something in the software, maybe an adjustment, and sometimes it's as easy as just clicking a button in the software to solve the problem. That's why it makes sense to remote connect to the PC of the system to check what's going on. And then, if needed, of course, a service engineer can go on site to fix the problem as well. But as always, the first step would be check what's going on remotely. And of course, for that, the customer will need some internet connection and remote connection software as well, like a TeamViewer, WebEx, or Microsoft also has some free solutions for that.
All right, and I'm assuming it's kind of like our other products where, simple questions. You got a little issue here or there. Just reach out to us. We'll help you out over the phone, like you said, remotely. Of course, if it's going to be a little bit more of an elongated procedure, then yeah, I mean, then we'd have to, look at whether it's a virtual visit or an in-person visit. And that extends also to application support, right? So like somebody has a little question about an application, just write it in, we can get back to you. If you're looking at deploying an all new method, on the other hand, well, then we do offer a service of application support, whether it's in person or digital, right?
Yeah, that's sure. Usually we receive emails as an application team. We receive emails from our customers and we answer them immediately. Sometimes it's just about a function in the software. Sometimes there's maybe something new that they want to add, maybe something to include in the calibration, change the calibration, some settings, that kind of stuff. And most of the time, we do it via email, and sometimes the customer just pick up the phone and calls us. That's also possible. And yeah, and it doesn't matter where they are located on the planet. So we can do this remotely without any problem.
But you offer also, let's say, application training on
site. We have two kind of trainings. Maybe I should say three with the new edition after the COVID. So the first one is on-site training. So we go to the customer side, which I'm going to do next week, in the following weeks as well. And the second one, we invite our customers to our application lab, so here, and to give them the training here on the actual systems. And the third one is a remote training over the internet. So we have all these options. So depending on the availability of the customer and the application teams and the distance, etc. So you can pick one of those options. Yeah.
All right, that's great. So another question has come in actually live during the stream here from Dachana. First of all, Dachana says, great show, Okan. So I think that's about your demo. Then, are there any options included in the Elemental Suite to control the spark stand clamp? We need an option to exclude the result option when taking the print without deleting it. Was there in Q matrix?
So the first question is controlling the sample clamp, right?
Mm-hmm.
So in the software, yes, you have two buttons to move it up and down. So if you press it, it will go down and touch the sample, and it will stop there, and it will not start the analysis. Yeah. So, and the second option, you can use the multi-purpose button to move it up and down. Again, you don't have to start the analysis to move it up and down. All you have to do is to press it just a little longer, and it will go down and touch the sample. And the second question, can you repeat that, please, John?
Sure. We need an option to exclude the result when taking the print without deleting. It was in Q matrix.
Okay. At the moment, when you exclude a measurement, it's only excluded on the analysis screen. But when you print it out, you print out all the results. But with the exclusion, if you print out as an Excel file, it's also excluded in the Excel file. Thank you for the feedback. I also didn't know that this was available in the Q matrix, but it's a good feedback for the software development team. I will definitely take this to our software development team to look at it.
All right. Another question that came in before the broadcast from Lily. Can I analyze different shapes with your spectrometer, things like wires, bolts, nuts, etc.?
Yep, that's possible. That's also what I showed in my video. So we have in all our instruments, we have different adapters for wires and sheet metals and all sorts of things. And these adapters that are compatible with the Q4 Tasman are also compatible with the Q6 Newton. And it's also an advantage if you're upgrading from Q4 Tasman to Q6 Newton, you can actually keep those adapters and use with the Q6 Newton as well. So thin wire adapters, thick wire adapters, metal sheet adapters, small piece adapters for bolts and nuts, that kind of small pieces. We have all sorts of adapters, and also the spark stand plate with the boron nitride disc to reduce the diameter on the spark stand. That's also one of the options.
All right. Now from Mike, it sounds as you have real factory calibrations on your spark spectrometer. Is it possible to include my own standards into your supplied curves?
Definitely. If you have some CRMs, we can also add them. It's quite easy process on the Elemental Suite. And all you have to do is just to go to calibration and choose the channel, and then you define your samples. So basically you enter the constant chemical composition information in the Elemental Suite, and then you spark that sample to collect the intensity data, and it goes automatically to the calibration. Then you just enable it to include in the calibration curve. It just takes basically a few minutes to include one sample.
And we have, I think you recorded a video also for that on brukersupport.com. You can have a look on it, and soon I think on the Academy as well.
Yeah.
All right. So from Dana, can your machines analyze oxygen in steel?
Not all, but the Q6 Newton can. Yeah, and of course Magellan can. But yes, the Q6 Newton has an LOD of 50 ppm in oxygen in steel. Yeah.
All right. From Barry, do you offer quick check programs like some competitors? How fast are they, and do these deliver all elements or only a subset?
Yes, we do. We have integrated, for example, for iron and steel, the Fe110 fast. That's the low alloy method, the fast version of the low alloy method. You get all the elements except oxygen, the one that you asked before, within below 17 seconds. So I think you used in your demo, you used this method, the Fe110 fast. So the normal one, let's say the standard one, is below 20 seconds. You saw the fast method is around about 2.5 seconds, even faster than the normal one. And we supply these methods also for aluminum base and also for copper base. In aluminum, it will be the global program, the 100 and 101 that have a fast version. And in copper, it will be also the low alloy one.
All right. And then one more question from Zoo. I need to export my routine analysis to a higher level QA/QC system. Can this be set up?
Yeah, it can be set up, and we have different options for exporting the results in the Elemental Suite. Some of them can be automated. So you can also do this manually, but if you're exporting the level 2 system like LIMS, and then you would definitely want to automate this. And then what we can do is you can export as a text file or a CSV file, and you can also customize all the exported file. So which elements you want, how you them appear to be in what order, and then which ones you want to eliminate, and all that information about the sample can be included in the exported file. Yeah, and LIMS automation is definitely possible for a long time. By the way, it has been available for a long time.
Yeah, but we can also write, I think, since a couple of months or years, even into another database directly. So if you, because the options mentioned so far are file-based, so you need file storage and store the file somewhere. And if you want it just electronically without creating data and store them in hard disk, you would write this into SQL database directly. That is also possible.
Yeah.
All right. So with that, we're at the end of our questions. Actually, one more just came in live. First from Dachana. There's two questions. So we'll do these two because they came in live. How it's possible to measure the oxygen with such a low wavelength?
Can you repeat it? I didn't got it acoustically.
Yeah.
There was a strange.
How it's possible to measure the oxygen with such a low wavelength?
With such a low wavelength? Why?
guess, how is it possible to measure oxygen in the Q6 Newton?
Okay. Yeah, the quick answer is just like any other element. So actually, it's not about as the trick is to find the right emission line here, right? So basically, in the solid state detectors, either CMOS or CCD, you put them side by side, right? And there are some limitations when it comes to, excuse me, to the wavelength selection and the positioning on the chip, right? So sometimes you may have to sacrifice something because the position of that emission line might be just in between the chips. Okay, if you can avoid that with the geometry of your optics, and you find the right emission line to analyze the element, whichever element you're talking about, and then yeah, you can definitely do it. And this is what we did with the oxygen as well. So that was no issue. And yeah.
There we go.
And you can even go down to 120 nanometers, for example, on a Magellan vacuum spectrometer. So and oxygen has emission lines there.
All right, and then is it possible to add a new base like nickel in the Q4 Polo?
Matrix addition on site, I believe this is what he's asking.
I believe so. Is it possible to add a new base like nickel base in Q4 Polo?
Q4 Polo. Okay. So then the matrix addition is technically possible, but the calibration is, I think, the biggest obstacle here, because as you know, when we calibrate the systems, we calibrate all the methods and ship the system with those calibration and those methods, right? And it takes a lot of time. And do this kind of complicated and heavy work on site is not easy, because you will also need a lot of standards to build up the calibration curve. So what we offer to our customers in that case, for most of them, they can ship the system to Germany, then we can calibrate the system. That's one of the options. And on the Q4 Tasman, we also have some other options that like matrix activation on site, but that's a different structure. But on the Polo, I think the only way is to
need to be returned to the factory.
To the factory. Yeah.
Because even if we do hand calibration on site, what about standardization? You need to be able to drift correct that matrix, and that is kind of fingerprinting, and that's only possible during the calibration. So.
All right. So, I mean, one of those situations, always feel free to reach out to us and we can get back to you with that answer for your specific situation. All right. So with that, I'd like to thank Peter and Okan for joining us today.
Thank you for having us.
Thank you for inviting us.
Yeah, the Q6 Newton really seems like a great addition to our industrial elemental analysis portfolio. And also, we'd like to thank everybody out there for taking the time to watch this and learn about OES and the new Q6 Newton. So until next time, we'd like you to keep your signal high and your background low.